Hello, new listeners, and welcome to Television. So, what's the deal with serialization? It can have a very significant impact on the performance of distributed applications, so it's worth giving it some thought. Let's dive in. Serialization is simply the process of converting objects into byte arrays. Anytime you move data across the network, you must serialize the data on the sending side and then deserialize it before it can be used. For a distributed application like Hazelcast, serialization is inescapable. But moving less data less often is a great strategy for improving performance. In episode 5, we covered lots of strategies for eliminating data movement or mitigating the associated latency, such as distributed compute, bulk operations, yada yada, async APIs, and so on. But ultimately, you'll be left with some amount of data movement that's unavoidable. And we're going to spend the next few minutes looking at how to make that movement as efficient as possible. Java has built-in support for serialization, and that serialization works out of the box with Hazelcast. So some developers will just default to using the path of least resistance. Not that there's anything wrong with that, but if you want to get the most out of your Hazelcast system, you'll want to know the secrets of more efficient serialization. The timing of when serialization happens is affected by how you choose to store data in Hazelcast, a setting known as in-memory format. There are three choices: binary, object, and in Enterprise Edition, native or off-heap. To see how this works, let's look at a simple get and put operation. When the client does a put operation, data serializes on the client side. If our in-memory format is binary, the serialized data is stored as is, without deserializing. In the diagram here, you see there's no deserialization step on the server side. When a get operation retrieves the data, that data is already in serialized form and can be returned without modification. The client then deserializes the data to get it into a useful format. Native in-memory format behaves the same. The only difference is that the data will be stored off the Java heap to avoid garbage collection. Now, if the data is stored in object format, the client-side behavior is the same. But on the server side, when we receive the data, we deserialize it into its object representation and store that. When the get happens, we'll then need to serialize the object at the server side before sending it back to the client. This is obviously adding more work on the server side, so why would we want to do that? If our only access to this data is to retrieve it by the key value, then there's no reason at all to go through this additional processing. But if we're going to query on our data values, then everything changes. So here we're doing a query. To evaluate the query, we must evaluate the deserialized value of the salary field. If the data is stored in binary or native format, we'll have to deserialize it. Depending on the serialization method used, we might have to deserialize the entire entry, or we might be able to deserialize just that one field. If the object is stored in object format, then we don't need to deserialize anything. And if the salary field has an index, we also don't need to deserialize anything, regardless of the storage format. So to recap, for binary data, we don't incur serialization overhead on storage or retrieval, get or put, but we do on queries. So binary is great for access by key and not so great for queries. For object data, we deserialize when we put the data, and we can then query without additional work. So if we're frequently querying, then object is better. Indexes avoid the need to deserialize on queries, but add some additional costs to put operations. So we've covered the what, why, when, and where of serialization, and that just leaves the which method to use. Hazelcast supports a number of different serialization options. Some of these are legacy or deprecated, so we're not going to cover every one. I'll refer you to the docs for the most accurate, up-to-the-current release info for every supported option. We've now reached the airing of grievances against Java serialization. Performance is just one of several criteria we'll use to evaluate serialization alternatives. Our first measurement is to look at how much space our serialized objects consume. Now, these benchmarks have been around for a while, but I recently reran them with Hazelcast 5.5 and Java 17 to see how things have changed. The code is part of the Hazelcast Code Samples project in our public GitHub repo, so you can look at the code and rerun it yourself if you care to. These numbers are based on specific data objects, so they might not correlate to what you see, and it's always best to do your own tests with your own data. In this first chart, we're looking at how much space is needed to store 100,000 test objects using various serialization methods. If you're storing data in binary format, then this directly correlates to how much space your data will consume on the server side. So inefficient serialization is really going to cost you. And the size of the data also proportionately affects the time required to send data over the network. So every get and put operation will take longer when using an inefficient serializer. Smaller is better when you're looking at these object sizes. Do they know about shrinkage? Note that Java serialization is 10 times worse than the best option, and about 5 times worse than the median. A somewhat arbitrary cutoff point might be to say that anything under 100 bytes per object, or 10 megabytes in total, passes this first filter and deserves further consideration. That reduces our options by about half. These next two charts show how much time is spent performing serialization and deserialization operations, and this is also for 100,000 entries. I'm not going to drill down into every one of these results, but Java serialization, again, is about 10 times slower than the worst of the good options, and about 40 times slower than Hazelcast JSON value, but that comparison is a bit skewed because Hazelcast JSON value still needs to be parsed through a parser to become useful. If all you care about is speed, then IdentifiedDataSerializable is the fastest, but it does have some other limitations, as we'll see shortly. Serialization operations are generally faster than their deserialization counterparts, but the comparative ranking is similar. Java Serializable, still the worst, Hazelcast JSON value, and Compact look like good options, and the third-party serializers are all reasonably good. The other options are so much faster than the Java Serializer that if you're used to using Java Serializer, you might think that these numbers aren't real. They're real, and they're spectacular. Performance is important, but it's not the only thing that matters. These are criteria you may want to consider. Your own use cases might not care about all of these, or you might have others that merit consideration. Now, we already looked at benchmark data that covers the performance aspect. For some methods like Java Serialization, you only get support for Java. So if you need to support non-Java clients, then choose an option that is language independent. Some formats will not gracefully handle changes to object layouts. So for example, Java Serialization will throw an illegal class exception if you try to read a stored object after the class has been recompiled with changes. Other methods can simultaneously support multiple schemas for the same classes, allowing for flexible versioning of our data formats. If you already use serializers like Avro, Cryo, or Protobuf in your application, then it makes sense to choose an option that provides interoperability. Some formats will require that you deploy classes representing your domain objects on each member of the cluster, or a third-party serializer could require deploying additional libraries on the members. These requirements may complicate your application deployment. As we illustrated earlier, if a serialization method supports partial deserialization, that can make your queries more efficient and also streamline data transfers when the transfer doesn't need to include the entire object. And finally, some serialization methods require custom coding or the configuration of factories. Some, like Java Serialization, require minimal code changes, just add implement serializable, and some, like Compact Serialization, have the option to work with zero code or config changes. So if you think about all of these considerations when choosing how to serialize your data, then you can truly be the master of your domain objects. Here are 4 options evaluated using the criteria we just discussed. I narrowed the options down to 4 just because they're in widespread use and because I couldn't spare the squares. Now, you've probably picked up that I'm not a fan of Java Serialization. JSON is fast and lightweight, and if your data is already in this format, then it makes sense to keep it compatible. Wrapping the JSON in a Hazelcast JSON value creates metadata from the labels that allow us to query the object contents, so it's better than just storing a string. Identified data serializable is the fastest of them all. If you care a lot about speed and you don't need interlanguage interoperability or schema evolution, and you're willing to spend a little bit of time writing custom serialization classes and configuring factories, then this might be the serializer for you. And finally, compact serialization. I feel this gives the best overall feature set. It can be completely no code, relying on reflection, or you can choose to write a custom serializer to squeeze out a bit more performance. It works with all client languages, can support version schemas, and works in coordination with the generic record feature to make it possible to avoid the need to deploy object classes on your cluster members. It's a Festivus miracle. Serialization significantly impacts application performance and capabilities, yet too many developers just go along with the default. You should evaluate options against your own data and with your own priorities, but at Hazelcast we've engineered compact serialization to provide the features we feel are likely to be important to a wide segment of our user base. In our next episode, we'll look at generic record. Generic record was designed to work alongside compact serialization, and we'll see how the combination helps make application deployment simpler and more flexible.